So far, we can find the values of definite integrals by using geometry or by constructing a Riemann sum. So to evaluate definite integrals and find the area under the curve, we use geometry if we can. Okay, and that doesn't always work. It depends on the function. Most functions it probably won't work. Or we can set up a Riemann sum, which is our limit as n approaches to infinity, sum of I equals 1 to n of f of xi star delta x. Okay, so geometry, we can only use it in certain circumstances. Riemann sums are really long and annoying to solve, just like when we use the definition of derivatives. So we would really like, just like we were able to do for derivatives, to find a shortcut so that we can evaluate integrals. So let's take a look at a couple of examples and see if we can find a pattern that might point us towards an easier way to do integrals. So let's find the area under y equals 1 from 0 to the point B. We're just going to pick a point and make it arbitrary. We'll assume B is positive for the sake of our picture. Okay, so we're going to find from 0 to B. This is the graph of our function. It is a horizontal line. Here's where we're stopping, and so the area we're finding is here. Okay, so we have a rectangle. So we'll write the area in integral notation. The area is the definite integral from 0 to b of 1 dx. So it's b times 1. The height, the width is b, the height is 1, so the area is b. Okay, so we have y equals 1. So the integral from 0 to b is b. Okay. Let's try something a little bit more complicated. I wonder what the integral of x is. So let's find the area under y equals x from 0 to b. So we have here, let's take a b here and a b here. So we're looking at this triangular area here. So this length is b, this length is b. Our area is the integral from 0 to b of x dx. And that's equal to 1/2 b squared. Okay, because it's a triangle, so b squared divided by 2, or 1/2 b squared. Okay, well, we've looked at 1, so a 0-degree polynomial. We've looked at x, a first-degree polynomial. So let's look at a second degree. So what about the area under y equals x squared from 0 to b? So let's take our graph. We have y equals x squared. We can draw on both sides. We're only going to be looking on the right-hand side. Let's make our b a little further over so I can actually color it in. What's the point of drawing area if you can't color it in? So up we go with our b. And then that's the area under our graph. Well, unfortunately, a parabola is not a circle. We don't have a geometric area formula for the area underneath a parabola. So our area, we can write it using integral notation, but we are going to have to find it. So the area is from 0 to b of x squared dx. We are now going to have to find this area using a Riemann sum. Okay, so we are going to, so remember we have the limit as n approaches infinity, the sum I equals 1 to n, f of xi star delta x. So we have to start thinking about rectangles. So first, the width of our rectangle. We're going to draw n rectangles on an interval of length b. Let's use a right-handed limit. Okay, we are going to use right-handed endpoints for our rectangles because those tend to be a bit easier. Okay, so our delta x is going to be b over n because the interval is length b. We divide it by n. Okay, so let's try to figure out what xi star is. So x1 is going to be b over n. x2 is going to be 2b over n. x3 is going to be 3b over n, because each time we're adding on another b over n. So our xi, and keep going, is going to be ib over n. So f of xi star, so if xi star is ib over n, f of xi star, we're squaring ib over n, is ib over n squared, which we can rewrite as I squared b squared over n squared. Okay. So now we can plug all of this into our lovely Riemann sum. So our area is the limit as n approaches infinity. Whoops, that's a sum. Jumping ahead of myself here. The sum I equals 1 to n. Our f of xi star is b squared over n squared, and I'm going to write times I squared here. I'm just pulling it off of the fraction because I know I'm going to want to leave my I squared inside the sum because that's one of my handy dandy sums I know. This is going to be multiplied by delta x, which is b over n. So I can combine all those b's and those n's, get that my area is still the limit as n approaches infinity. B and n are both constants for our purposes. We left b. B is going to be part of our answer because we left it as a variable on purpose because we want to take an arbitrary constant. And n we're going to deal with when we get to the limit. So b cubed n cubed times the sum I equals 1 to n of I squared. And we know a shortcut for that sum in terms of n, the sum from I equals 1 to n of I squared. So this is the limit as n approaches infinity of b cubed over n cubed times n plus 1 times 2n plus 1 all over 6. Okay, so we see this n here. We can cancel that to be n squared, which is lovely. And now we can expand our numerator. So this is equal to the limit as n approaches infinity. And I'm going to pull the 6 out to the fraction in front because it'll probably be happier there. We have b cubed over 6n times 2n squared plus 3n plus 1. I feel like we've done that expansion a few times here now. So this is equal to the limit, and we're just going to now expand our brackets here. We can actually take that b cubed. So you see how this b cubed, it's not the variable we're taking the limit over either. This was an arbitrary constant, so we can treat it as a constant. So I'm going to pull the b cubed outside that limit, and we'll just multiply our answer times b cubed. So this is b cubed times the limit as n approaches infinity. So now 2n squared divided by 6n squared is 1/3, plus 3n, so that's 1 over 2n, and 1 over 6n squared as we distribute our denominator. Now, as n goes to infinity, that goes to 0, and that goes to 0, so we are left with 1/3 times b cubed, or b cubed over 3. Either way is a valid way of writing it. So let's see if we can see a pattern from all of this. So let's look at the 3 examples we looked at. So we have f of x, and we have the integral from 0 to b of f of x dx. X squared, we get 1/3 b cubed. X, 1/2 b squared. And that would be like an x to the 1. X to the 0 is just b, or 1 is just b. So we notice the power is going up by 1, and we're dividing by the new power. So one of the things we can think about when we look at this is actually, if we looked at b as a variable, what would happen if we took the derivative of the right-hand side with respect to b? You would get b squared, like x squared, or you would get b, like x. You would get 0. Or you would get 1, like 1. So what we notice is the derivative of a big f of x dx is equal to our little f of x. So there's some big function that we get that's equal to the derivative. So we can define an indefinite integral f of x dx equals big f of x plus c. So we're going to have, this is called the antiderivative, which is the opposite of the derivative. And this actually, as we continue going on, we're going to talk about the fundamental theorem of calculus. And the fundamental theorem of calculus is what links the idea of backwards derivativing, or taking the antiderivative, to finding the area under a curve, and what we've been doing with our definite integrals and Riemann sums so far. So it's linking those two things. We have a couple other words in this big, super duper important statement here, which is, this is called the constant of integration. And what the constant of integration is that when we integrate, when we find an antiderivative, we don't actually know which antiderivative we have. So if we're taking the integral, we're going backwards from taking the derivative. If you have two functions like this, and let's say you have function here and the same function just down here, these two functions, if you have like f of x and then f of x plus a, they both have the same derivative because the derivative of a constant is 0. So anytime you add, you're only adding a constant, you would still have the same derivative at every point. So when we're taking the integral, we've lost the information of where what that constant might be. So we have to add a plus c just to show that we're not quite sure what the vertical, whether there's been a vertical translation, because if you take a function and translate it vertically, it still has the exact same derivative at every point. So when you underderivative, you're not sure if there was a plus 4 or a minus 7. So you have to add plus c because any of those could be the correct answer. Okay? We also call this piece right here, the function that we're integrating, the integrand. So, let's take a look at this in algebraic form. So we have the derivative of x squared plus 5 dx. What's that equal to? 2x. The derivative of x squared minus 10 dx is equal to 2x. The derivative of x squared plus pi minus 1 over radical 3 divided by 17 dx is also equal to 2x. So the integral of 2x dx is equal to x squared plus c. And it is just any constant, so we don't know. So this is what we call a family whose derivatives are 2x. And unless we know something about the starting point of the original function, we actually can't get that information. We don't know which one it's going to be. And so what we're doing is we are right here. You notice I didn't put from a to b or from any point to any point here. I just had an integral signs. We don't have any limits of integration. So an integral with no limits of integration is called an indefinite integral. And it's indefinite because when you find the integral, you're always going to have that plus c. And if you're wondering, Miss Eaton, would you take off marks if I didn't write plus c for an indefinite integral? You betcha. That's what makes it an indefinite integral, is that you don't know whether you're adding a number, what number you're adding, how big, subtracting. It's impossible to know. So we have to add the plus c because there's a whole family of functions that your answer could be when you're finding an indefinite integral. Okay. So we are now going to find a few indefinite integrals. And essentially what you are doing, I wrote find a few. That was my say it, not my write it. Find the indefinite integrals of, the integral of x to the fifth dx. So when we're finding these indefinite integrals, we are finding the antiderivative. So we're finding the function whose derivative gives us this. So we're doing the opposite of what we did with the power, because we have a power, we're doing the opposite of what we did with the power rule. So we are increasing the power by 1 and then dividing by the new power. Okay, so what we did, if you remember for derivatives, we multiply by the old power and then drop the power by 1. Here we do it in the opposite way. We increase the power by 1, then divide by the new power. So the integral of x to the fifth dx is x to the sixth over 6 plus c. Okay, you can also write it as 1/6 x to the sixth. You can multiply by the reciprocal of the power as well. And if that's a fraction, that might be easier. So the integral of x to the minus 7 dx. Well, we're going to up the power by 1 first, so x to the minus 6. And then we are going to divide by the new power, divided by minus 6, plus c. C, the integral of 2x cubed dx. Well, we're going to up the power by 1 first, x to the fourth. The 2 stays there, then we're going to divide by our new power, so it's 2x to the fourth plus c, which is 1/2 x to the fourth plus c, when we simplify. D, let's look at the integral of 6x to the fifth dx. This is equal to 6x to the sixth divided by 6 plus c, which is just x to the sixth plus c. And if you notice, hey, I could just pick that 6 back up as thinking as you do in a differentiating way. You don't necessarily have to write out the intermediate steps. So E, let's try the integral of 4x to the fifth minus 3x to the minus 2 dx. Remember from last time we have our integral rules that you can just take the integrals of each term separately. So this is equal to, I'm going to up the power, 6, divide by 6. We get 4/6, which is 2/3 x to the sixth. Second term, we up the power, that's minus 1. And we are going to divide by minus 1, which just gives us a plus 3 x to the minus 1, and then plus c. And we always have that plus c no matter what. If we are doing an indefinite integral, that's what makes the integral, indefinite. So x to the n dx, integral of x to the n dx, is equal to x to the n plus 1 divided by n plus 1 plus c. And so now we can integrate absolutely any. We can do it with trig functions, etc. As long as you know the derivative, as long as the function you have is the derivative of another function, you can take the integral.